Welcome. Good afternoon. Okay, so I posted a bunch of stuff. Let me see if I can kind of crop this. Well, I don't want to crop out my joke. I'll leave that in there. Okay. So I struggled big time. It took me all weekend to tame this one programming problem that I had. It's not for you to worry about, and it's not something that you'll have to deal with. So, but I just couldn't figure it out. So that's why I got the lab out late. But I know you guys are getting caught up on the other labs, so hopefully that's okay. And so what I did was I posted some assignments. So I've broken it up into simple linear regression, which I'm pretty sure a lot of these questions you've seen before. And so especially if you took Stat 230 with me just last term, then you've seen some of these, and that's just a refresher, right? To kind of say, oh, okay, we know this stuff. And then I posted a multiple linear regression assignment. And I think these are all due on Sunday. This Sunday? No. Yeah, I think so. So these are all due on Sunday at midnight. It's always midnight. Okay. So the lab, what makes it a lab is you have some data and you have to work in R or whatever method you want, but presumably R, and to kind of work through some of those questions. It's working with linear regression, right? So multiple and simple, but nothing about splines or anything like that. We're gonna save that for probably a different course, right? You guys take a regression course, I think. You'll see plenty of that then. Polynomial regression, right? All that fun stuff. So we're gonna focus on the core concepts. Okay, so in the second assignment, do you mean the multiple linear regression assignment? Yeah. Okay, the per ounce and per pound question. I'll have to have a look at that because I don't remember that one specifically, but I'll make a note of it here. So the per ounce per pound question on the multiple linear regression. Okay, I'll have a look at that. Okay, so last week we finished regression. There's lots more to do, right? But last week we had an overview of linear regression, right? So we had an overview of linear regression. Okay. Right, for a continuation, you'll do regression with probably Claude. Claude teaches it. I don't know if you're taking it right now at the same time, or if maybe it's later on in your kind of schedule. I can't remember. But more techniques. Oops. Are covered in your regression course. I always loved it when there was overlap in material, right? Especially if it's being covered at the same time in multiple courses. So so hopefully that regression part was kind of like, oh, I know this. Okay, so one thing that we need to remember is that regression, when do we use regression, or the term regression rather? We use it when we are predicting numerical variables, right? And so that's a huge thing that we want to do. If I want to predict the sales that I'm making, if I want to predict, you know, how much I can sell my house for, if I can predict how much is my company going to be making in 5 years, that kind of thing, right? It's all money related, notice. If I want to predict, I don't know, I can't think of anything but money related problems, right? But that's okay. Think of something else. I want to predict, it's all money related. All the examples that I can think of are all money related. Anyways, it doesn't matter. Numerical data, right? And so recall, so regression has a numerical outcome. Numerical outcome is modeled / predicted, right? And so it's a numerical outcome. So now in chapter 5, we're going to start talking about classification. Now, classification is the term that we use for if we have a categorical outcome. Okay. So chapter 5 is on classification. And excuse the multiple colons here, but it's when we have a categorical outcome is modeled / predicted, right? So classification is for categorical data, whereas regression we use for is the term that we use for numerical data. Where it gets a little bit fuzzy is we are usually going to use logistic regression for classification, right? So don't be confused there, right? Logistic regression is a form of classification, so it is for categorical data. Okay, gets a little bit boggy. Okay, so so notice, right? That's a really important, a fundamental difference to keep track of, right? Once you have those, then you can kind of apply them accordingly, right? Of course, as long as you know how to classify your variables as numerical or categorical. Remember way back when we spent all that time, or I felt like we spent all that time figuring out, is this numerical or is it categorical? Is this numerical or is it categorical? And then flash to now, well, it's going to dictate how we're going to analyze this thing, right? And so it's really important to kind of go back to the basics and know what type of variable you have. One thing is that we're going to focus on binary outcomes, 0, 1 outcomes. But remember, a categorical variable can be reduced to a binary variable. So any categorical variable can be reduced to a binary variable. Okay. So we focus classification, or we focus our classification techniques on binary outcomes, right? And so that's categorical with only 2 categories. Now I'm going to put the 2 in little quotation marks because I might have more than 2 categories, but there's only 1 category of interest, right? So with only kind of two categories. Right? So a 1 is the category of interest. Oops. Category of interest. And the 0 is whatever the categories that are not of interest. Categories. I didn't do that very nicely. Category / categories. How about that? Not of interest. Okay. I noticed I started a bracket, but I don't know where to end it. So I'm going to remove it here and just do an arrow. Okay. Even if you have multiple categories of interest, then what can you do? Well, you can let each category be the category of interest, but you're going to have to fit multiple models. Right. And of course, there are other ways that we can deal with it. But for these techniques, right, we're just going to focus on one binary outcome for the most part. Okay, so even with multiple categories of interest, right, we would build the models individually. So even with multiple categories of interest, even with multiple categories of interest, we would build models considering each one individually. We would build models considering each one individually. Right. And then we would consider a series of binary models. Right. And so here, this is to say, consider a series of binary models. Okay. All right. So what we're going to find is that for a 0-1 outcome, so let's just focus on 0-1 outcomes, and the outcome that we're modeling is always going to be the 1, right? And so we will always model the 1, the category of interest, right? Otherwise, it doesn't really make sense. It's boring, right? And so we will always model the 1 category, right? Or sometimes we'll call it a case, right? So the 1 category or case, right? That's the thing that we're interested in. So it makes sense that we're going to model it. Now, with all these techniques, what we're going to get is, and so just as a heads up, right, where we're headed is we're going to talk about some of the different models that we could use. And I would say that for me, at least, the model that, has come up the most is logistic regression. But it's good to have a good handle on some of the others just in case. But that's why I'm going to kind of zip through naive Bayes and LDA. and kind of focus on logistic regression, right? But of course, the textbook talks way more about them, but it also focuses on logistic regression. So I'm not alone in kind of, okay, that's the front runner. But it's also because I come from a kind of a traditional statistical background, and so it relies on a sampling distribution and blah, 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 which I know it's not cool, but it is a thing. It's a thing I do. Okay, so here we go. So we're always going to model the one category. Now, our model is not going to tell us, oh, that's a 1, oh, that's a 0, right? Unlike the numerical outcome, we were able to get, oh, the predicted value is this, right? So unlike regression, the model will not yield the predicted value, will not yield the predicted outcome, I'll say predicted outcome, right? 0 or 1. Rather, in this case, right, for all these models, they're going to yield the probability of being in group 1. Rather, each model, oops, each model will yield a predicted probability of being in class 1. Will yield a predicted probability, oops, of being in class 1, right? What's the probability that this outcome is a 1? Okay. And so you probably have this kind of this thought train going on. Okay, well, if I have sample data, then I could build my model, and then I could check my actual outcome against my predicted outcome. But how are you going to decide what your predicted outcome is, right? You're going to use that probability of being in class 1, right? But also that means that you're going to have to decide on a threshold, right? If the probability is greater than this value, I will classify it as class 1, right? So there's a little bit of work that you have to do before you can kind of get there, right? But if you think about the logical process that you would go through, right? Okay, so I predict if it's class 1, and then I can compare it to, okay, well, was it actually in class 1? And then those are the tools that we're going to use to evaluate our model, right? But that's going to be, we'll wait for next day to do that. But if you've taken 300 already, I feel like at the very end of Data Science 300, we talk about these, but it's at the very end, so you have to rush through it. So we're going to take a little bit more time, a little bit. Not a lot more time, because I do want to get through the whole textbook, but chapter 7. We'll see. Okay, so where was I? What was I saying here? Okay, so therefore, so I shouldn't say therefore out of the blue. To classify an outcome, right? Or to classify a predicted outcome, I should say, as class 1 or class 0, maybe we, not I, we we will need to establish a cutoff, right? And depending on what we're talking about, right, maybe that cutoff is anything, if the probability of being in class 1 is more than half, right, more than 0.5, I'm going to put it in class 1, right? Maybe there's a cost associated with saying that it's class 1, right? And so I want to be sure that the probability that it's in class 1 is quite high. Then maybe, you know, the probability has to be greater than 0.8. So it's going to depend on what we're talking about, right? But if the cost of misclassifying is low, then you can reduce your threshold, right? So to classify a predicted outcome as class 1 or class 0, we will need to establish a threshold or a cutoff value, right? Where we kind of say it's class 1, right? And so here, remember some probability facts, probabilities range between 0 and 1, right? We remember that. Okay. And remember, the probabilities are the probabilities of being in class 1, right? So specifically here, probability of being in class 1. So, for example, if the probability of being in class 1 is more than 0.5, right, I might say that, okay, these guys are in class 1 and these guys are in class 0. I don't know if that's the case, right? That's the whole goal, is I'm trying to figure out, okay, how can I try to predict what class I'm in without knowing what class I'm in? Right, I'm thinking about school classes. Anyways, so if the probability of being in class 1 is less than 0.5, you would probably say it's in class 0, right? Whereas if the cost of misclassifying, right, because even if the probability of being in class 1 is 0.6, right, there's still a 0.4 chance or a probability of being in class 0. So it's still a possibility, right? And so we can increase the threshold by so to ensure that the probability of being in class 1 is really high before you put them in class 1. So we can increase the threshold to ensure the probability of being in class 1 is high before we classify as class 1. Right, so the other option is if you have something like this, right, 0 to 1, and then what if we only let anything, the probability of being in class has to be 0.8 or higher, right? Now all of these guys are in class 1, and these guys are, of course, in class 0. So it's not always a 0.5 cutoff, right? That just kind of divvies them up, right? It's the most intuitive one, right? For example, if I told you that so without having some sort of cutoff, right? If I just told you that, okay, the probability of being in class 1 for this outcome is 0.7, what does your brain do? It says, well, I better say it's going to be class 1, right? Because the probability is higher than 0.5. That's what your brain is doing, right? But if we want to be really sure, then you would alter it to 0.8 before you classify it as class 1, right? Okay. So some of the methods that we can use, and they all have kind of different tweaks that we can do. And so I'm just going to talk about them in general. But of course, software builds all these models, right? So, so here we're just going to talk about in general what they do, and then we're going to apply them in the lab, okay, or on Friday, if I can get it to work by then, hopefully. Okay, so let's see here. Okay. There are some kind of common models, classification techniques that we can use. So there are some common classification techniques or classification models we can use. Okay, we're going to outline just the general idea of them here. Okay, and then we're going to apply them with software, right? And so it's just to have an idea of what they're doing and how they differ, but very brief overview. We will provide a brief overview here. But in the real world, right? We will use software to apply them. So R, of course, to apply them. Okay, so it's going to be a little bit discombobulated, but it's good to have seen them beforehand. Okay, we will focus on logistic regression. It's kind of the most common one, but it's nice, right? If we want to build a couple of different models, it doesn't hurt to consider some of the other methods. Now we're going to be able to build many different types of logistic regression models. So there's not just the one, just like linear regression, right? We can add predictors, we can take away predictors, we can have interaction terms. Same thing applies for logistic regression. So there's lots of models to be had from just logistic regression, right? But it's nice to just kind of, oh, and there's these others in case I ever need them. But for our purposes, we're going to zip through them and go to logistic. All right. And so the first one is the naive Bayes. Now, there is such a thing as the exact Bayes, and what the exact Bayes does, and I'm not even going to write about it because it's crazy, or like, I guess I shouldn't say crazy. It's so needy, let's say, that it's not something that we would do. So the exact Bayes does this. It goes, and if you have some set of outcomes, and what we're going to assume is that we have categorical predictors, okay, and so that's one assumption that we're making. Remember, if you have numerical data, then you can make them categorical, right? If you have age as a variable, that's numerical, right? But as soon as you make age categories, you have categorical data, right? So I'll jot that down when it comes up again. But for now, let's talk about exact Bayes. So what it does is we have some set of predictors, and I want to try to figure out what the class is. So what it does is it goes through the entire data set and finds all the outcomes for those exact predictors. That's nuts, right? Especially if you have, so that's fine if you have two predictors, right? X1 and X2, right? So you try to find someone with, you know, the same X1 and the same X2, and you might have 3 different outcomes, and 2 out of 3 are class 1. So then your prediction is class 1, right? You majority rules. And so, but what you'll find is that, okay, well, that's not really that great, right? And so, because what if you want to predict something and that exact combination of predictors doesn't exist in your data, then what, right? So then we move to naive Bayes. Naive Bayes looks at the probabilities, okay? And so naive Bayes, it estimates the probability that xj, so the probability of xj, so the probability of a predictor, so any predictor x, and then xj, x1, x2, x3, x4, right? However, for j predictors, j is the number of predictors, or maybe I shouldn't say that because that might get confusing, right? It's not the number of predictors, but it's just to indicate, well, it is, but to indicate any predictor. So I'm going to not write that down. The probability of xj, given that y is some outcome I, where I is 0 or 1, right? So what we can have is, so the outcome, we're going to focus on 0 or 1, but of course we could extend it to multiple outcomes. But like I said, we're going to focus on 0 and 1. So for example, if I want to know, okay, if the outcome is 1, right? So if it's a 1 case, right? Then what's the probability of being in of that predictor, right? So the predictor variables are also categorical, right? So, and so usually they're binary, right? And so you're going to have some probability when you look at all the y equals 1 cases, and then where xj is equal to some number, given that y equals 1, for example, right? And so then you have the conditional probability of x1 equal to 1, for example, okay? And you can think back to, now this isn't necessary, right? But I just want to link it back because you do know how to find this. So the probability of xj given y equals I is the probability that xj of xj and y equals I. Oops, clean that up. Made that look weird there. Divided by the probability that y equals I. Right, that's the conditional probability. Probability of A given B is the probability of A and B over the of B. So we've done that before, but that's not something that we have to worry about, right? And so I guess what I'm trying to show you here is that there's a lot that goes into the naive Bayes, but then it's just one click of a button in R, or not a button, but one line of code that you need essentially, and then it'll just do it for you. And so you can kind of tune out if you want to, or not. Okay. So we're going to find a probability, a conditional probability for each x, right? So for each predictor. So this finds finds a conditional probability for each predictor. Okay. So then what you're going to do is you're going to multiply those probabilities. One thing that we're going to talk about, or not talk about rather, not talk about, but here I'm going to talk about it, is that we're going to assume that, so the reason it's naive is because we're going to assume that they're independent, right? The predictors are independent of each other, which means that I can just multiply those probabilities together to get the total probability of those things happening together. That's not really true, right? That's naive to think. And so that hence the name, right? But it is something that we do, and it's something that kind of, it tends to work. So that's okay. So then what we do is, so here I'll just kind of say step 1, step 2 is to multiply these probabilities for all the predictors. What does this is where the naive comes from, is it's naive because we assume independence. Okay, that's what's naive. Your third step is to do this not just for class 0, but also for class 1. So you're going to repeat this for both cases, right? And so now repeat these steps for the other class, right? 0 or 1. And maybe I'll clarify, I equals 0 or 1 equals 0 or 1, right? Because here we decided to pick just y equals I, where it's either 0 or 1, and then you can find the probabilities, the conditional probabilities. You're going to multiply those all up, but those are all for one of the cases, right? Starting with 0 or starting with 1, it doesn't matter, because then you're going to repeat with the other case, right? So now you're going to have these conditional probabilities for either of the cases, right? Or these total probabilities. Now, so you're going to repeat those. And then step 4, let's call it, is divide all those by whatever class you're interested in. Okay. So divide all the multiplications and maybe I'll refer to step 2 here. So divide the probability from step 2, probability. How can I not spell probability all of a sudden? I just need to not think about it. Probability. What a weird word to not have to, or not be able to spell right now. Anyways, so divide the probability from step 2, of whatever case you're interested in, right? Usually case 1 of the case of interest. Case 1 usually. Because if you know the probability of case 1, then the complement is the probability of case 0, right? So we only need to focus on one of the probabilities, and then we have the other probability, right? And so, right, remember that video that I posted? Half do or half don't, right? So if you know one, you know the other. So divide the probability from step 2 of the case of interest by the sum of the probabilities I guess for both cases. Right, we can extend it to more than 2 cases, but we're going to focus on just 2. And like we've talked about, right, a lot of these things can be reduced to just 2 cases, so it works just fine. Okay, so by the sum of the probabilities for both cases. So really what we're doing is, okay, the probability of case 1 divided by the probability of case 0 and case 1, right, which is all the possible outcomes. Right? Same idea that we've seen in the past. And then this yields the probability of being in case 1 given those predictor variables, right? And so then whatever the probability is, right, that can help me assign which case. So then use the probability to assign the outcome to a case, depending on what the decided threshold is. Use the probability to assign the outcome to a case depending on the threshold. One thing that I want you to note is that this assumes that we have categorical predictors. Okay. Assumes, and this is where I'll write down what I was talking about earlier, where I said, okay, that's not an issue, right? Because numerical variables can easily be turned into categorical variables. However, categorical variables, we usually can't turn them back into numerical variables, right? We get these lumps of numbers, if anything, right? And so, but it's easy to turn numerical data into categorical, right? So it assumes categorical predictors but any numerical predictor can be kind of turned into, I don't want to say transformed because we don't multiply or divide or do anything by it, but we bin them, right? So any numerical predictor can be binned to create a categorical variable. In terms of programming, right, you never want to change your actual data, right? You want to add a new variable so that you can go back and forth and use them, right? So that's kind of a rookie mistake, is that you alter your original data, whereas you should just be adding a new column where you're making your categorical variable, right? Because that way you can check to make sure that it's doing what you thought it was doing, right? And also make sure that you don't have any overlap in your categories, right? You want to start one where the other one ends, right? And so just kind of things that are just going to come with practice, right? It doesn't help that I say them, although if it happens to you, I think your brain is going to be like, I know she told me about that. She told me this would happen. I just I had to get there on my own, and that's how it is, right? So I'll say it, but it's not until you're there and you've made those mistakes that you're kind of, your subconscious is going to bring you back here and say, yeah, she did say that. That was a problem. Anyways, and then you learn, and then you grow. All right. So so we assume that we have categorical predictors. So you can bin them. Another option that we're not going to really look at is we could use distributions, but let's just kind of ignore that, and let's just go for the basics of just kind of binning our categorical data, because I think that makes sense, right? So age, so the numerical variable might be age, right? Whereas the categorical variable might be age groups, right? Notice can't turn categorical data into numerical. All right, so it doesn't go the other way, just one way. It's a one-way street. Okay, I gotta pick up the pace here. All right, so naive Bayes, I know it feels like we haven't really talked about it, but I will apply it, and then what you're going to end up with is a probability of being in class 1, and then you use that to classify, right? And then we'll talk next day about how do we evaluate those models, because that's its own thing, right? What makes a good model? Okay, so Fisher's a famous statistician, and I can't remember anything about him right now, but I mean, fun to look up. But Fisher's linear discriminant I feel like the F in an F test is from Fisher, but I might be wrong there. Is the other kind of modeling technique that we're going to look at. Okay, but again, we're going to kind of fast forward to logistic regression. So Fisher's linear discriminant, it looks at, so it considers the covariance or the covariance matrix, right? And that's another one of those things that you'll see more of when you take regression, or that you have seen more of in regression, right? And so the covariance matrix is basically just a supersized version of the standard deviation or the variance, right? The variance looks at one variable, but now we have two variables that are trying to move together. And so what's the variance there? Okay, and so that's the covariance matrix. But what it does is LDA, as it's called. So LDA is the A is for analysis. And maybe I'll write that instead here. Linear discriminant analysis, LDA. LDA maximizes, and what it considers is the within sum of squares versus the between sum of squares. So if I have multiple groups, right, then the sum of squares is really a measure of spread. And if the spread between the groups is quite large, right, but the spread within the groups is quite small, then I have these kind of distinct groups. And with those distinct groups, I can apply probabilities, or I can find and predict probabilities of being in each group, right? And so it kind of maximizes the distance between these two things. And of course, you can read the textbook for kind of a more meaty description here, but in general, it maximizes the between sum of squares and minimizes the within sum of squares. So the groups, the spread within each group, right, should be quite small. They should all be very similar, right? Case 1, they should all be very similar. Case 0 should be all very similar. And here are the most common kind of features that I have. And minimizes, oops. The within sum of squares. Okay. This gives us the greatest separation between the two groups. So this gives the greatest separation between the two groups. Right, and so LDA, we want to try to maximize the SS between divided by the SS within, right? If the spread between the groups is quite large, right, then I have these distinct differences between the groups. And then if the spread within the groups, that's great, because now that distance, that large distance between the groups, it actually means something, right? Because everything within the groups is so small. So you're trying to maximize this fraction, right? And so it maximizes, and maybe I'll bump this over here, maximizes the SS between and SS within, where the SS is a measure of spread. Right? It's kind of pretty, kind of a little too basic way to say it, but I do think that it helps to think about it that way. Right, and so it maximizes that distance between versus within each group, and using the covariance matrix. Oops. Right, and the covariance matrix is the variance, but the variance between two variables, right? So it's kind of similar to the correlation between two variables, right? Because we have kind of between 0 and 0, right? So if I'm looking at two categorical variables, right, two binary variables, then I have 0, 1 and 0, 1. So I have some variance between 0, 0, and that's the variance of 0. Right, and then 0, 1, and then 1, 0, and 1, 1, and they're all going to have different variances, and that's in the variance or the covariance matrix, right? So it's just an extension of basically the standard deviation, if you want to go that far. All right, but of course we apply these, and then we never look back, and we don't have to worry about it. But one thing that I want to note is that LDA technically assumes that you have these normally distributed continuous variables for your predictors. So that's unlike the naive Bayes, where we had these categorical predictors, right? But what we would find is that okay, so in theory, it relies on having these normally distributed numerical predictors. However, right, what we're going to find is that in applied situations, it can handle some non-extreme non-normality, right? So as long as it's not too extreme, it can handle it, right? So it's robust to that normality assumption. But also binary variables. Remember, binary variables tend to a normal distribution as we increase the sample size, right? From binary distributions, we remember that sort of maybe, right? And so it kind of makes sense that that would happen. But LDA technically assumes approximately normal continuous variables or continuous predictors. Assumes approximately normally distributed, predictors but in an applied setting it still works, but in an applied setting it still works for slightly non-normal predictors as well as binary predictors. For slightly non-normal predictors as well as binary predictors. Okay, so that's kind of cool. Okay, so let's talk about logistic regression. And I know that you've probably seen, potentially, it depends on kind of where you are in the program, but you've probably seen logistic regression at some point already. And so, of course, you know that there's a little bit of theory that we need, but I'm going to kind of gloss over it because we're going to do the applied version. So our last kind of technique that we're going to focus on is logistic regression, or at least in this chapter. So logistic regression, not to be confused with regression on its own, right? Regression means that we have numerical outcome, whereas if we say logistic regression, then I have a categorical outcome, specifically a binary outcome, right? But in general, categorical. Okay, keep those straight. So if we think about a 0-1 outcome, right? So if we focus on a binary outcome, then, and maybe what I should say here is categorical outcome / binary outcome. Okay, so what we could do is just for a little bit of background, right? If we have a scatter plot, right, of the class on the y-axis, and then on the x-axis I have maybe x, right? So I have some predictor variable x, maybe x1, right? So some predictor variable x1, and what we're going to find is that we're going to find that, and I'm going to increase my point size. Maybe this is too big, but yeah, too big. Okay, so what I'm going to find is that I'm going to have these kind of points here, and depending on the spread within the predictors, right, maybe there are some predictors of x1, right? So x1 is on a numerical scale, right? And so now, and we can look at binary scales too, but let's focus on the on the continuous scale. Oh man, words. So here I have class, oops, 0. My other option, I only have 0 or 1, right? And so my other option here is that, okay, and then some of these guys are 1s, right? And so there's this kind of murky area where, right, same predictor gives 2 classes, right? That's where it's going to get difficult to classify, okay, just based off of that predictor. So now we're going to find the probability of being in class 1 or class 0. So of course, if your X is somewhere in this region, then that probability, right, is going to be close to 0.5, right? It could go either way. So what can we do? What are some of the tools that we have? Well, I could model this with a straight line, right? And that's something that we do. I say, okay, well, I want to use a straight line, right? But it doesn't look like I should be using a straight line. So how can I tweak it to be able to use a straight line? And so that's what we're going to be doing. In terms of terminology, when we do that, when we say, okay, I want to use a linear model, it doesn't look like I should be, but I want to, and I think I can make changes to my data so I can transform my data to make it happen. That's where the term generalized linear models come from. Okay, and so it's logistic regression is kind of a special case of that, right? Where I have some idea and I want to use the linear model things that we learned in chapter 4, so just basic regression, right? But now I want to use it for something where it's not obvious right away, right? And so here, we could, right? I could fit a linear model, right? I could do that and try to use it to predict the values. So it would do a decent job of predicting over here and a decent job of predicting down here. But other than that, it's going to do a terrible job of predicting, right? Especially because it's going to predict for classes between negative infinity and positive infinity. And that's not going to work for us, right? But technically we could, but it's just going to be a bad model, right? So we could use a linear model, right? But it would give us a bad model. But it would give us a bad model, right? Bad predictions. That's what we mean when we say it's a bad model. It means it doesn't predict well. Okay. So you could use a linear model, right? But we're not going to yet. Okay. So instead, what we're going to do is we're going to talk about something called the odds. Now, it's a huge pet peeve of mine, but it's also something that you're not really expected to know from grade school and stuff like that. But when you say odds, the odds are actually the probability of something happening over the probability of it not happening. Okay, so odds, so we will transform the predictor, or sorry, the outcome which in this case is just 0 or 1, right? Into a numerical outcome that can be modeled by a linear regression. Into a numerical outcome between negative infinity and positive infinity, which can be modeled by a linear regression. That's kind of cool. So I put an exclamation mark there because it's really something kind of fancy that we can do, right? And so I wanted to talk about the transformation and how it gets there, but the transformation relies on the odds. Okay, so the transformation relies on the odds. Okay, and so the odds is the probability of something happening over the probability of it not happening, which is 1 minus p. So the probability of the event happening over the probability of the event not happening. Okay. In fact, we model the log odds, and when we take the log odds, then I get this extension from negative infinity to positive infinity. And so that's kind of cool. And so because I need more time, that's okay. We model, so ultimately, we model the log odds or sometimes you might call it the logit, right? So if you see those, they're interchangeable. So ultimately we model the log odds using a linear regression. Okay, and so what we have is we have the log of the odds. Technically that y equals 1, right? The probability or the odds that you're in case 1. And so you want to really keep those separate, right? Because the odds uses the probability. It's not the probability anymore. Okay, so the log of the odds that y equals 1, right? So the event is y equals 1. So the case 1 outcome is going to be modeled by beta naught, oops, clean that up. Beta naught plus beta 1 x1 plus beta 2 x2 plus all the way up to, let's allow for beta q xq variables. So here, now we can use a linear model. From chapter 4. That's back into familiar territory, right? So that's good news. We know how to find these coefficients. I can check the p-values to figure out what predictors should be in my model, right? All those things stay the same, right? But the problem now is interpreting these predictions, right? But the predicted value is now the log odds. Okay. So kind of maybe in red is that the predicted values are now log odds or the logit, right? So in order to find the actual predicted value, right, or the predicted probability to find the predicted probability we need to basically undo the log odds, right, to solve for that probability. So you can go through and you can work through mathematically what that would look like, right? You know what the log of the odds are. The log of the odds is the log of P over 1 minus P. And then if you're trying to solve for P, then you can work through that, right? You have some predicted value that is the log odds. So to find the predicted probability, we need to undo the log odds to solve for P. Okay. So what that ends up looking like, I'm just going to give it to you. P is 1 divided by 1 plus E. So of course the log, just as a note, right, forever forward in your life, in terms of statistics and data science, presumably, log means the natural log, right? There is no other log unless you're in physics or something like that, okay? And so here, this is the natural log. Log base E, so that's how when we undo it, we have to use E, right? And so E to the negative y hat, maybe I should make that bigger, right? So this model behaves the exact same way that other models, other linear models, right? So I can find the coefficients, I can find estimates for these coefficients, I can plug in values of X, but it's going to give me some Y hat, right? So where Y hat is, and maybe I'll use beta naught hat plus beta 1 hat X1 plus beta 2 hat X2 plus beta Q hat XQ, right? And so these are the predicted estimates, or sorry, the estimates for the coefficients in your model. Once you plug in the values of X that you're interested in predicting, right, then you get some Y hat, and this Y hat comes from here, right? So this is really 1 over 1 plus E to the negative of the whole model, right? So so once you've plugged these values in, you know how to do that from chapter 4, right? But now we take it one step further, and my predicted probability, so it still doesn't have a class, right? Because we have to say, okay, any probability greater than 0.5 is going to be in class 1, right? And so, but once I have the probability, then I'm smooth sailing. I can classify it however I want, right? And so it's a little bit more work to get that probability, but we got to leverage the linear model, which we know and love. Okay, I think that's where well, that's all the time we have. So that's where we'll end it today. And we'll pick up on evaluating these models next day. Okay, if you have any questions, let me know, but I'm gonna stop this recording. I'll see you on Thursday.